Okay, hi everyone. Thank you very much for joining today. But before we start, we want to make sure that everybody of the speaker is in here. Because I want to make sure the Beijia Juan is in here.
Yes, I'm
Oh,
here.
okay. Thank you very much. Okay, let's get started. Okay, thank you. Right. Uh, Welcome everyone. I'm Hiroki Tanikawa of the Nagoya University. This is ISIE SEM Perpetual Online Conference, Session 6, January 2021. Welcome, everyone. I hope everybody being safe under the current circumstances around COVID-19 situation. On behalf of the all board member of the SEM, I'm really welcome all of you to joining here online via Zoom and also the YouTube. We originally planned the physical 2020 ISIE-SEM conference in Sendai last year in Japan. But as you know, it's because of these situations, we are very difficult to make the physical online physical conference. So we, as a board, we are discussing that we try to make the online conference not only one time, but also the monthly conference, monthly perpetual online conference from the last summer. So so that's why we put on the title of our conference of perpetual. That is, we are trying to have a monthly short special sessions, and we are trying to keep continuing to promote our conversation between the SEM members. And also that this session, perpetual online sessions is totally free. So everybody who are not the ISIE members is also can join this online sessions. So that if you have any feel interesting about our sessions, and if you still not the member of the ISIE, so please join the ISIE and please join our SEM group, Socio-Economic Metabolism section. So today we put the session theme names toward sustainable material stock. I'm very welcome. I'm very happy to having the 4 excellent speakers who are listed here. And as you know, actually we are now in the socio-economic metabolism section. Our section is sort of we need to think about the material flow and also the material stock as well. So as you know, the material stock is another side of the coin to the material flow. So we need to think considering the both stock and flow simultaneously for sustainable development. So in this session, we focus on the material stock of our society from many aspects. For example, the indicator system, and also the material, and also the modeling, and also the life cycle or cities impact from the material metabolism. So today, we are inviting 4 speakers: Tomer Fishman from Israel, and Ippei Maruyama from Japan, and also the Raud Maudrana from France today, and also the Beijia Huang from China. So I hope you enjoy, and also I hope you all have the fruitful discussion, and also the wonderful idea from the speakers. And each speaker has a 15 minutes presentation plus 5 minutes question and answer time. And after whole presentation, we will keep the time for the general discussion as well. So I want to invite the first speaker, Tomeo Fishman. Tomeo, how are you?
Hello, Hiroki. Thank you very much for the introduction.
I will quickly set up my screen share. Please let me know if you are able to see it. And
Yes, I can see now.
okay, great. Um, so I guess I should start. Um, and my apologies for pointing down. That's where my other screen is. It's one on top of the other. But the topic that I would like to present about today is about a new framework of indicators, numeric quantifiable indicators that we have developed in order to um, try to explain the relations of material stocks and flows to service provisioning. Um, this is specifically the product of very long-term work about the material stocks of the built environment, with a focus on construction materials, but also all other materials that are in use by society, as well we can see here in this macro level picture. This is specifically from Tokyo, a picture that I took a few years ago. That encompasses all of the materials that basically we are interested in. Of course, not in their raw form, but rather in the um, products and goods that they compose. The work that I'm going to be describing to you is coming from a recently published paper. You can see written by a very big team that I was very happy and proud to be a member of. And since this is already just published last month, basically, the year is 2021 though, but in case you haven't seen it yet, um, you can use the QR code here to um, go and take a look. I am also adding the um, full bibliographical information now in the chat box, so you can click the link there and read our paper. Highly recommended. Very nice paper in my humble opinion. But the starting point for our work is that in recent years there has been a very big advancement in industrial ecology and beyond in the study of material stocks. We already know a lot of answers to questions that we have about material stocks. For instance, we have been doing a lot of research, not just us and our group, but in industrial ecology in general, about where materials are being stocked in a very high level of detail, of spatial detail. This is an example of a study that we did in Japan, another study specifically for road materials in Vietnam, and another recently published paper that goes down to the level of individual buildings across more than a century in Tiaxi in China. Um, so we have been making, as a community, very big advancements in that regard, in this question. We have already been advancing the questions of which materials are being stocked, building up more and more information about the material intensities of different types of materials. In the examples here, in buildings worldwide, including the distributions and the statistical changes and variances across different locations, but also of different types of vehicle technologies. And we have also been busy as a community looking at the question of what's the future of the stock, using very different approaches and methodologies, both for the global level, for specific sectors in specific countries, such as in this example, vehicles in the United States, or for wind power and specifically for neodymium, a specific material in a specific sector in a specific country. Um, there are so many papers being published on these types of stocks related research nowadays that it's becoming hard to catch up actually, and that's great. And in our new paper, we are presenting a new account, a long-term account of the flows and stocks of Japan from 1990 to 2015. So that's 25 years. looking at the changes in the flows and the stock across this very long time period. This is the first time that, to the best of our knowledge, we have a combination of both the flows as documented in the economy-wide MFA, EWMFA standardization, plus the stocks. So the stocks are explicitly quantified. They're not a black box of just changes to the stock, but the entirety of the stock itself. And we see lots of interesting patterns thanks to that were not available before. For instance, we can see that that consumption, overall inflows, have been decreasing dramatically in Japan in those 25 years, mostly thanks to decrease of domestic extraction. You can see here that imports are more or less the same, fluctuating up and down. The water accounting balancing item is not changing dramatically. So it's mostly domestic extraction that has been dramatically decreasing to nearly a third in 25 years. And most of this improvement is not because of throughput materials, which you can see here are not really changing much, but rather thanks to less new additions to the stock. From 1 year or one period to the next, there is less and less new additions to the stock. However, the removals from the stock are more or less fixed at more or less equal rates throughout the entire time period, which means that we have more additions to the stock than removals from the stock. That's a net addition throughout the entire period, which explains why the material stock itself is still increasing throughout the entire period, and in fact has been nearly doubling itself in this time period. We can also see other interesting things on the outflow sides. The total outflows, turns out, remain similar throughout the entire 25-year period, mostly because throughputs are not really changing. Throughputs are materials that are used within 1 year, but also the removals from the stock are not changing dramatically either. However, the changes that are very clear are in the outflow streams. There has been a dramatic shift to more recycling, nearly no final disposal. It has gone down in an order of magnitude. But other types of outflows, such as emissions, materials used for food, fertilizer, they have been remaining more or less the same. We can also see here that the balance of which materials are stocked and for what use, which materials in red, the use type in shades of blue on the right-hand side have been changing. There has been a much bigger increase in roads and their material stocks compared to slower increase in other categories. Now, the question that remains after we see that we know a lot more about the numbers, but the question that remains, the big one, I think, for us as a research community, is why do material stocks accumulate? There are lots of reasons, and this is a very complex issue because it involves, first of all, the relations and uncovering the relations of socioeconomic development, physical development. We need to understand what the drivers of material stocks actually are. We want to understand what the long-term dynamics and paths of accumulation would be across the development pathways of different countries, both developing and developed ones. And we want to eventually figure out whether material stocks actually stabilize and reach saturation. And how do we even quantify saturation? Is it per capita? Is it on an absolute level? Or is it saturating, or would it even decrease eventually as part of maybe a degrowth movement or something like that? And in practical terms, can we improve the efficiency, material efficiency of the materials that we already have? Can we minimize inflows to have less impact on the environment from the extraction side and to maximize circularity? Um, Specifically in this paper, we wanted to use the new data that we created to look most explicitly at the two first questions. And the question that arose was whether we actually have the right indicators to really answer these types of questions. In order to look at that, we went back to the literature to see what has been done in recent times. Um, and what are the roles of material stocks? So we um, say that material stocks are in between. They are connectors between the environment and impacts that humans do on the environment, and connect also to the social economy. From the environmental side, material stocks, well, to build them up, that means extraction of materials from the natural environment. They alter the natural environment, the landscape and land use. They involve lots of inefficiencies and hence wastes. They require throughout their material cycles, their entire life cycles, material inputs, energy inputs, which means emissions in our current energy systems, throughout both extraction, production, use, and end of life, and other environmental burdens such as toxicity and particulate matter and other impacts are involved in them as well. On the other hand, from the perspective of the social economy, they provide fundamental services, which some people may call maybe functions. Things like dwelling space, transportation, communication, and other socioeconomic needs are provided by these artifacts and goods and products. They are capital in the classic economic sense, a production factor, but also containers of investment and resources. And the way in which they are constructed and the way in which they are used and even their locations dictate the lifestyle and life quality. Um, and this understanding has been around in industrial ecology and beyond in sustainability sciences and has been developing. And recently, well, it's by now it's nearly 3 years ago. A very nice paper by O'Neill and colleagues um, was talking about quantifying a good life for all within planetary boundaries. And they actually presented something very similar to what we have here in the title. On the one hand, there is the biophysical resource use. On the other hand, there is the social outcomes. And then in the middle, there are the provisioning systems which bridge between these two aspects. They are the link. And you can see here, they actually say the physical provisioning systems are infrastructure, technology, manufacturing, that's material stocks, but also our social infrastructure, like government, communities, and markets, and so forth. This was quantified very nicely in that paper, but they specifically wrote that they do not know how to quantify the provisioning systems and integrate them. So in that paper, they compare for different countries the resource use and environmental impacts to social outcomes, but the bridge, the middle part, is missing. However, they, as you can see here in the caption for this figure, they base their framework on the ends means spectrum from Herman Daly, which was developed by Donella Meadows. We actually found that independently, but it turns out that it links together. So what was that paper? That was a report from 1998 by Donella Meadows, the systems scientist, um, known from the limits to growth and so forth, where they actually tried to quantify and understand whether we can come up with indicators for sustainable systems. The front page has this flower, but in truth, you can see that it has roots and leaves and a flower at the end, but inside the report itself, they actually use a triangle. It's just easier to look at, which they call the Daily Pyramid, named after Herman Daly, or the Daily Triangle. And that's the one that we tried to use here. So let me just quickly go over it in case you haven't seen it before. The Daily Triangle basically starts with, at the bottom, the base on which everything is based is the natural capital. Those are the ultimate means of the planet. Those are the natural resources, land use, ecosystem services, and so forth that are there in nature, in the ecosystem, basically. From these, humans derive, through consumption of materials and energy, intermediate means. That's the build capital that we have. These are things from all the way from food to build up stuff to products. Basically, all of our physical stuff is converted from natural resources into, well, products and goods, buildings, infrastructure, and so forth, and accumulate as the build capital. Um, the reason for accumulating these things is supposedly in order to provide with intermediate ends, social capital, things like health, education, security, economic welfare, which is measured by GDP, and so forth. But these are not the final, this isn't why we want to have these things. They are also intermediate ends, which in turn serve to provide us with these services for human well-being, things like life satisfaction or fulfillment. These are the ultimate ends. And once we look at that in such a pyramid, we can start looking at specific cases and see how they actually fit this. Let me show you a few examples. Say we start with a house. You can see here in the picture, it's a nice North American style house. Um, it's in order to build it and to well use it, we need resources from the natural environment, construction materials, materials that provide us with energy to give electricity and heat or to cool it down throughout its use. So that's the link right there. The flows that are needed in order to construct and manage and run, operate the house. Supposedly, by living in a house, we get all these benefits, all these services that the house provides. Clearly, first of all, it's a shelter or dwelling, security, hopefully. But it's also, it has value, it's a wealth, it's an investment, so ownership as well. And depending on the house, its location, its the size, style, what it has inside, it's also social status, which is another social service that is gained from owning a house or living in a specific house. That in turn is supposed to provide us with what we need as humans to have well-being, happiness, satisfaction, success, a sense of self-fulfillment, and so forth. Obviously, if it's such a house in our modern capitalist societies, that's it makes sense to us. And if we say replaced that house with this one, even though maybe in terms of materials it's more or less the same amount of materials per square meter, maybe, but obviously we are not gaining the same levels of service provision from such a house. And even maybe we are actually saving up on materials here, but we are failing to meet these ends, both the intermediate ends, and hence it fails to meet the ultimate ends as well. Um, Another example maybe could be a car, an SUV, for instance. It requires different types of materials to build it up and to use. But it provides us again with different services, mobility, transport, social status, and wealth again. Hopefully, again, to provide us with these ultimate end services. However, as I think many of you know, if you've ever been in a car, usually that's not the picture that we have, right? When we're sitting in a car, we don't think about these lovely balloons and everything. It's more something like this. So there is a failure here, a serious failure in the provision of these ultimate ends from these intermediate means. So why are we keeping to accumulate all of these materials as cars if they end up just making us more miserable? The question is, now if we have this framework, can we quantify these things? Because if we can do so, then that means that if we can get more of these ends, by using less of the means, that would be decoupling, true decoupling. So we tried to come up with indicators that would help us to quantify this. Um, and this is the set of indicators that we have developed to look at this. First of all, we try to use ones that are already in existence. Material productivity, for example, which is usually GDP to inflows, um, is already out there. It's popularly, commonly in use. It's meaningful. We understand how it works and what it means, and we have values for this for many, many countries. Of course, it doesn't have to be GDP. It could be things like Human Development Index to include more things, not just economic activity. It doesn't have to be direct inflows. It could be material footprints, for example, so that we can associate the indirect material requirements of a country. But it's already there. And that relates the ultimate means to the intermediate ends. However, we can also look at other indicators that already exist, such as the stock productivity. How much economic activity do we gain per unit of material stock that we already have? That relates to the classic production function in economics of capital providing us with economic output. And then there's also an indicator that's not commonly in use, but it's mentioned here and there, of the stock retention time, the balance between how much material stock we already have to the inflows. That tells us something about the lifespan of the stock, or the balance between how much inflow we need to maintain the current stock or to build it up. Um, that would be measured in years, usually with our type of data. And then we came up with a few more indicators, such as the primary material use rate, which is also becoming more common for measuring circularity, how much primary material inflow, domestic extraction, or other virgin materials are used out of the total share of inflows. A smaller number means more recycled or circular use of materials, which is supposedly a good thing. And up there at the top, we could have service productivity, the balance between, say, how much benefit we get from the services that are provided to us, say, welfare to GDP, for instance. However, that's a bit more difficult to quantify. It's difficult to quantify happiness or well-being or quality of life. So we could also skip it and make material productivity go all the way up to the top by replacing GDP with one of these more social indicators. But this means that we end up here with a set of indicators, not too many, as you can see here, but they include all of the different levels. They link up all of the different levels of this daily triangle. And we tried to use it for the data that we compiled for Japan. Not all of the indicators could be used in this case, specifically the ones that are for the ultimate ends. But even so, we came up with these figures. And as you can see here, material productivity in Japan has been increasing very nicely in this period, which is a good thing. So more economic output, using less raw materials. Of course, some of them are, if that was compared to the footprint, not to the direct inflow, it would not be as rapidly increasing, but that's for a different discussion. Primary material use rate has been decreasing thanks to more cyclical use. Stock retention time has been decreasing. And stock productivity has been decreasing too, which is not very good, because that means that we the stock is not being used as efficiently as it could be. But what we can do with these data is take it even one more level up and combine them together. The indicators that we came up with are designed to be linked up in order to be used for the composition analysis, like IPAT, basically, in which the material productivity can be explained by things that happen within the pyramid. And then using oh, sorry, that sound means that I should end up soon. Um, we can see here through this index decomposition that we have done, we can show how the improvement in the material productivity, which as you can see in the triangle there, skips a few stages. It can be explained by the following improvements to the stock retention time and improvements, but not as big, to the cyclical use. However, the inefficiencies of the usage of the current stock actually bring down the material productivity. It could be better. This is a good tool because now it not only links everything together, but it can also be used for policy. We can tell policymakers or decision makers now, from the perspective um, of what needs to be improved. Where can we focus our efforts in order to further improve material productivity, further decouple economic activity from resource consumption? This shows us where we can make the most focus. Obviously, GDP per stock, the stock efficiency, that's the big gap. That's where we need to make improvements. How will we do that? That's for the next study. But this is one big step towards doing that. And in conclusion, this new framework that we came up with is, to the best of our knowledge, the first operationalization to quantify this means ends framework, including the entirety of the framework without skipping any stages. It allows for decoupling on individual steps within the pyramid, but also from all the way from the bottom all the way to the top. And it can be used for other types of services, like sector-specific ones: dwelling space, passenger kilometers, hours of screen time for electronic devices, for instance, and specifically with functional units, reference flows, if we want to make comparisons from LCA. Can be plugged into this framework and used instead of economy-wide ones, like the ones that we show here. And the SDGs, whether purposely or not, I'm not sure, but the indicators that are part of the SDG framework fit very nicely in the various levels here. So we can also use them and explain them using this framework as well, and the changes over time. And well, the first manuscript that describes this framework is now published. So again, please click the link or take a the screenshot of the QR code. And we have more coming specifically for different sectors to show how this can be used, not just for the economy-wide case, and not just for the Japanese case. So please stay tuned. Thank you very much for listening. And if you have any questions or comments later, I'll of course be very, very happy to answer them.
Okay, thank you very, very much, Tomer. It's a wonderful presentation. So now it's open for us. And so if you have any questions and comment to Tomer's presentations, please raise your hand. And also, it's also available to, if you have any question, to put it in the chat box of the Zoom. So anyone here? Right, so well, Tomer, thank you very much. actually, if you have the any idea for the next step, if you think that you are talking about for another countries or for another step of the indicator systems, please let us know if you have any plan.
It's yeah, exactly. It's a great point because it's well, in Japan we are working on specifically for the case of buildings, which would enable us to not only look at the building stock, but also how many of the buildings are actually in use. So that would add another indicator um, that not only talks about how much stock is there, but actually whether the stock is at the right level. Um, and our paper actually describes that option. It shows how that indicator would fit into this framework that I presented. But since for the economy-wide case, we didn't find a good indicator for that, I skipped it here. But at the next project that we're now working on, that is specifically going to be a part of it. Um, but as always, it's a chicken and egg problem. Now that we have these indicators, using them elsewhere, the challenge is to have good data. We need data for all these different uh, individual uh, values in order to make these composite indicators that fit together. So if you have data and want to try and use this, please let's get in touch and do it together. I see
All
that
right, thank you.
Stefan has a question.
Okay, thank you, Tomer. Now we have the question from Stefan Parik. Are you there?
Yes. Hello. Hi, Toma. Hi, Hiroki. Thank you. This was really, looks like really good work and also very inspiring. My question here was about the material scope, right? The first plot you showed, the stock and flow combined, that you have the throughput materials. Does this include also fossil fuels? And in how would you expect the results to change when we disaggregate between stock building materials like metals and concrete and the throughput materials? Thank you, Toma.
Yeah, thank you for the great question. Maybe I'll share the slide again so we can look at it while we talk about it. Um, the throughput materials here are, well, for energetic uses, basically, and other consumables that are used within a single year. Um, so that means it's a combination of both fossil fuels for energy, so plastics, the ones that are long-term plastics are going into the stock. Short-term plastics like single-use bottles or cups are also throughput, but the majority of the throughput is indeed for energy, either for electricity or heat, for energy for our goods and the material stocks, but also, as you can see here, some of it is for food. So it's energy for humans and livestock as well. Um, and that in part also shows us that since throughputs have not been really changing in Japan in these 25 years, there is a big opportunity right there by changing, for instance, the efficiency of the energy provision system or switching to energy systems that are less reliant on fossil fuels. There is a very big opportunity right there. Um, and of course, that links back to, since these are energetic uses to provide energy to our stocks, that involves a shift in the stocks as well. So it all fits together very nicely. And I think that these types of figures help us to communicate uh, these aspects to people from outside our field, but also inside. Does that answer your question, Stefan? Or
Partly, yes. And I think there's also more uh, uh, opportunities to think. For example, one could take the Sankey diagram and maybe have two colors, one for the cyclical material use and the other one for the throughput use or something like that to also
that's
show the difference. Yeah,
yeah.
but it's really cool. Thank you.
Thank you very much.
Okay, thank you very much. maybe you have some more questions, but it's a bit time constraints. So we still keep the time slot for the rest of this session. We will have the general discussion. So if you have any questions, please give us in the very last of this session. Okay, thank you very much, Tomeo. Wonderful presentation. So then I want to invite Professor Ippe Maruyama from the University of Tokyo. As Tomeo said, we are thinking about material stock and also for the sustainable societies. But think about for the stock itself, we need to think about more for its materials component. Actually, the Professor Ippe Maruyama is doing a lot of work for the concrete materials. So I want to invite Ippe Maruyama, Professor Maruyama. It's your time, please.
Thank you very much, Tanigaro-sensei. Today I would like to talk about some information, what we are doing for the, excuse me, I will, this one. As the Professor Tanigawa introduced, I'm a material engineer dealing with mainly the cement and the concrete. I would like to talk about the sustainable view on the construction process and how we are dealing with in Japan. So regarding when we're talking about the eco-friendly concrete or concrete structure, what we have to think about? So, we have to think about the pollution abatement, also the energy saving and the environmental protection, the global warming, urban heat island, and recently we have to think about the nanomaterials and waste. So there are plenty of the issues which we have to take into account. For these objectives, we built some. We make some rules or recommendation for the building stocks. The first, in the Architectural Institute Japan at the 2000, we built the Global Environment and Architecture Charter. This is just, we make some consensus and the philosophy for the construction in Japan. And after that, we make some system to evaluate how much the target building is eco-friendly. We call it CASB, probably you may know. So this is a comprehensive assessment system for building environment. Now, at the same time, regarding the material flow, the LIME has been developed. And after that, the late, excuse me, 2003 regulation of environmental consideration published from the AIJ. And also we published the environmental friendly construction guideline 2008. And after that, the consideration implemented in this Japanese standard is proposed to the ISO activity. So, there is many conflicts when we want to take into account the many things, many issues for eco-friendly construction. For example, if we try to save the materials, we try to use recycled materials. But in general, when we produce a recycling material for construction, it is very expensive and high energy consumption. So it is very difficult to to satisfy these two things. So we make the 4 categories for eco-friendly construction. One is resource-saving type, and the next one is the energy-saving type. The third one is the environmental load-reducing type, and the finally the long-term use type. So these are the category for eco-friendly, environmentally friendly the construction, but the target and objectives are different. So now currently we are doing how to satisfy the multiple objective through the construction process and also the material development. So regarding the concrete, you are much familiar these kind of things rather than me. So in the construction section, we use many the consumption and also energy, and also we produce the global greenhouse gas emission from the construction section. So we have to think about the things. And regarding the construction material, cement is one of the biggest the material. I mean, so this is the largest manufactured production on Earth by mass, and the second most used industrial substance in the world after the industrial use water. And so the engineering bridges, dams, architecturally innovative skyscrapers, roads, railroads, high-rise apartments, so everything, none of these will be possible without cement. So we really use the cement, But when we think about the cement production, still the production rate is increasing. About 90% of cement is currently and will continue to be produced in non-OECD countries. And as you see, so almost the cement production is constant in the future in OECD countries. But you see that China will make a peak around 2020 to 2025, and then gradually increase. But the production in India compensates the reduction of China, and still we see the increase in cement production in India. And also the Africa countries is waiting. So they are producing a large amount of cement. So, but at the same time, the production of ordinary Portland cement, the cement, generates about 800 kilogram of CO2 per ton of cement, of clinker, of cement. So the fossil fuel conversion is responsible for about 40%, while the limestone decomposition, so calcination, is responsible for 60%. So actually, the energy is not the problem. To get the calcium resource from the nature is our concern. So we have to think about how to make the construction material without the CO2. So, but when we think about the boundary condition of the material for construction, there is a limitation. So when we think about the earth chemistry or the element in an earth crust, the silicate, aluminate, and the ferrite and calcium is the major components. And all of these are included in the cement. So it means that the cement is almost optimized the production from a viewpoint of the earth chemistry. And when this is the the typical oxide composition of the modern cement, or ordinary Portland cement. So calcium silicate is a major part of the element, and other of these are aluminum and ferrite. So it is now we have to think about how to make the alternative cement without the carbon CO2 production. So, but to make the cement, to make the binder for the construction material, we have to think about the several required the properties. So for example, we have to make the very low density material, the hydrates, the reaction product with water is very important because it make a low density material. So if once we make the low density material, the space filling performance is become much better. So we need the hydrates in general. But at the same time, the ions forming the hydrates must be able to migrate from the original particles into the previously water-filled space. So once it is dissolved, and then we have it become it should be precipitated in a free space. So this is also the important issue to fill the space to make the construction material. And the hydrates themselves must have low solubility. So this is one of the required character of the material. Because of the low solubility, it is easy to precipitate in a free space where originally water occupied. So when we mix the solid with water and make the hydrates and fill the space and make the stiffness or the strength. So these 3 points are very important. So we have to select the material based on these requirements. So at the same times, we also have to think about how to reduce the CO2 emission from the making cement or making the construction process. So this is, I borrow the PowerPoint from the Duncan Halford. This slide has been already published in 2008. And he mentioned that in the cement industry have to take these kind of the means. So first, we have to improve the fuel efficiency to make the cement. And the next one is we have to use the recyclable energy. And then we have to switch the switch the fuel for the like a thermal recycling process. So also they have to the cement industry have to make the better efficiency of fuel, and they also they have to use the nuclear and the renewables, and then but still 20% cannot be decreased without the CO2 captured at the underground. So that is why the cement industry want to keep the CO2 underground. Otherwise, currently it is very difficult to satisfy the required value for the CO2 emission. So in the World Business Council for Sustainable Development may establish this roadmap. So they speak, they conclude that the cement industry have to think about the energy efficiency field, clinker substitutions by mineral additions and supplementary cementitious materials, and carbon capture and storage or use. So actually, in Japan, the energy efficiency is almost the idealistic condition. So there is no room to improve. And regarding the fuels, the modern cement kiln is a very flexible machine. And in Europe, the use of waste as fuel can be as high as 80% of the thermal demand. So it is almost the maximum capacity the European country use. And as I mentioned, the calcium and shrinkage is a very important material for the construction material. So the people try to use the other resources for the calcium and silicate. But so, for example, we are thinking about we are using the fly ash from coal-fired power plant and the blast furnace slag from the blast furnace plant, and also limestone filler. But in near future, the coal-fired power plant will be shut down, and also the steel industry want to use the hydrogen to get the iron from the ferrite. So probably these kind of the supplemental cementitious materials cannot be used. So therefore, alternative binders, additives should be found to compensate, to reduce the ordinary Portland cement amount for future. So now the cement industry doing the research on these things. So for example, they try to make the low calcium amount cement. So we call it B-light rich or B-light element the clinker. And also we are using the hydraulic calcium silicate clinkers, or we try to replace the calcium with magnesium and make the magnesium-based cement. But actually, the amount of magnesium is very limited. So probably this is not be the solution for the solution for universal. And at the same time, some researchers doing the research on the carbonation handling cement. For example, when we use the gamma type, this is the shape of the crystal, the B-light. This material can react with CO2 to make the low density calcium carbonate to fill the space. And so in some cases, these binders can be used for the concrete. And also, we are try to use the many kind of byproducts. And also, we are, especially in Switzerland, they try to use the calcined clays. So when we burn the clays, and it became reactive, and this, as you know, the clay contains silicate aluminum, and it is easy to hydrate. So therefore, the calcined clays are used for the as additives. And also, for example, the volcanic glass can be used for the reactive material for cement. So this is a really natural resource. So some the country start to use these kind of materials to reduce the cement amount. And at the same time, some people are doing the alkali activated materials and geopolymers. So when we use the liquid glass to react with, for example, metakaolins, we can make it's a kind of we see some geopolymerization, meaning that make the network by using the inorganic material. For example, the aluminum and the silicate has the 4 arms to connect each other. So when we add the silicate and aluminum, and then by and when they connect to each other, we see the inorganic mineralization, polymerization. So, but this material is not can be used for large scale. So still there is a large limitation for the application. To currently to solve the CO2 emission problem, almost all the cement industries make some internal consortium, which is called as the Global Cement and Concrete Research Network, and they make funds and call the researcher to make a proposal based on their requirement and make many the research projects. So all the cement industries are now tackling the problem or for tackling the CO2 emission problem. So I would like to introduce several the recent activities in the society. So as I mentioned, the Professor Karen Scribner from EPFL is recommended to use the calcined clay limestone cements, as the clay is quite a general material found in many countries. So the calcined clay and the limestone can be used as additive for cement. And as since the used ordinary Portland cement amount is reduced, so this is the one of the sure and the favorable pathway to reduce the CO2 reduction. But it's very difficult to stop the CO2 emission because this technique still require the ordinary Portland cement. So the other method is proposed by the Heidelberg Cement Company. So, so as I mentioned, the calcium and silicate are very important material for the construction material. And these the material can be found in glassy materials and byproducts. So first they mix these material with ordinary Portland cement and then wait for a long period to react with, to make the reaction inside. And after that, to capture the CO2, they, after the demolishing the concrete structure, they try to make a reaction with the CO2. We call it the carbonation. Now, after carbonation, we will find many calcium carbonate as a result of the reaction of calcium and CO2, and at the same time, many carbonates are found. So, and these kinds of things can be easily calcined and become easy to become the cement. So the first, the glassy materials used in a building to wait for a long period. Now, after reacted using the carbonation process, they make the good original material for making the cement. And then once the cement is used for the building, in this case, the CO2 is almost neutral. So therefore, this is not zero CO2, but this is a sustainable, this can be a sustainable cement. So this is one of the pathway to reduce the CO2 with the sustainable building construction. So finally, I would like to introduce the how to make the building sustainable, or how we can use the building for long term. So you know, when we make the construct some building, there are many requirements. In Japan, we have to, especially we have to think about the earthquake performance. This is very important. So we generally make the building against the requirement of earthquake. So we put some safety margin, and the performance of building is something like this. And the figure is a relationship between the performance as a function of time. And when we see the some continuous the hydration process, the performance will be increased. And at the same time, after the some reaction with the environmental materials, we see some reduction of performance, for example. And at the same time, when we have the large earthquake, based on this experience, sometimes it will increase the requirement performance. So always we have to think about the requirements and how the building performance is. So, but at the same time, now the current problem is how to evaluate the real performance of the concrete structure, because in general we just think about the design state and we just put safety margin and we don't think about the aging the deterioration process. So it means that we cannot predict the performance in the future. So now we need some scientific knowledge about how the material changes under the given environment. So we have to think about the weather, earthquake, typhoon, tornado, volcano, and also we have to think about the used materials. And also, it is very difficult to find the relationship between the chemical reaction and the physical property, because as you know, the many people dealing with the chemistry, but and many people doing some physics. But in construction, we have to we need the both actually after the reaction and how the physical property changes. That is very important. But actually, this kind of knowledge, we had a large gap between the required thing and the current state. So we are doing the scientific work for the prediction of the performance of concrete structure. I would like to introduce some recent progress about this. This is the article about our journal paper. So we generally, recently, we found some rare materials in rare material, which is called the aluminum tobamorite. It's found in the thick concrete wall in a nuclear power buildings. So the tobamorite can be found in nature, but the people think that the tobamorite can be formed more than 100 years or 1,000 years, or I say the geological scale. But based on our recent the research, we found that the rare material, which means that the very rare, the natural crystal, which is very stable and the durable, and make the concrete concrete strength development. So now we are investigating how these kind of materials was formed in a nuclear, the thick concrete wall in a nuclear power plant. And then we found that the reaction pathway is very similar to the Roman concrete. So now we are investigating how to promote this reaction in the modern concrete. That is the one of the recent activities of ours. And at the same time, we are trying to learn from the nature. So, this is a kind of fossil. This is actually the calcite, calcium carbonate, which formed around the shell. And we found that the mechanism of this. So based on this, we can try to gather the calcium carbonate from the nature and make the concretion. So now we are trying to apply this reaction pathway to heal the cracking in the concrete structures. And this is the last one, which I'd like to introduce. So in United States, Utah, we found the ferrite the concretion. So you see, we can find the ferrite shell in the field. The people call this the sorry, I forget the name. The people and the similar things can be found in the Gobi Desert and also on the Mars. So recently, we found the reaction pathway why this ferrite shell can be formed in nature. And this process can be applied to gather the desired element, from the nature. Now we are trying to apply these kind of things to make the natural shell in the underground. So this can be applied for the shelter in the Mars, for example, or some nuclear waste disposal. So as the summary, the large mass for new infrastructure is necessary in near future, but we have to prepare for it with the new technology to reduce CO2, energy consumption, and material consumption. So I didn't mention that, but we also have the large mass for old infrastructure, and this should be revived. So the appropriate new pathways for material for infrastructure can be possible by learning from nature. So, but we should think time is on our side. So the planning for the reaction is needed. Thank you for your patience and attention. Thank you very much.
Okay, thank you very, very much, Mariyama Sensei. It's a quite interesting talk, which is we need to think about for the, not only from the whole material metabolism, but also for the very interesting aspects from the material itself to think about for the sustainable society. And also the quite interesting to think about for the reviving infrastructure, reviving concrete. So this is a new aspect for me as well. So now open for floors. So any questions and comments to the Mariyama, Professor Mariyama? Okay. Alright, so. Okay, but we still keep the time for the general discussion in the very last part of our sessions. But Mariyama Sensei, could you tell us more about the reviving technologies up to date? Is it possibilities for installing to the real industry?
Yeah, for example, reviving it's not it's not renewal, but we have to use the infrastructure for a long period. So in that case, for example, we need some reinforcement. So it's quite a general technique in Japan, but at the same time, so when we think about some hazardous environments or the specific environmental condition which is harmful or the difficult to survive for concrete infrastructure. So in that case, we need some special technique by using the coating, for example, or reinforcement or partial replacement, or anything can be possible. But it is a little bit expensive. But I think we have to think because we cannot just throw away the infrastructure, because we have to use that is infrastructure continuously. So we have to think about the new technology to revive the infrastructures. So now, for example, the healing material is now used in the concrete structure, but in general, it requires a very humid condition. So, some people try to use the bacteria to fill the concrete crack, precipitating the calcium carbonate or other minerals based on the small lives in the concrete. So now we are doing the possible, investigating the many possibility to revive or to use the infrastructure for long period.
Thank you very much, Marima-sensei. It's quite interesting to think about for the reviving and also healing the damaged concrete as well. Okay, thank you very much, Marima-sensei.
Thank you.
Okay, so maybe maybe if you have any questions and comments to the Marima-sensei, please type in to the chat box as well, and then maybe we will have to keep continuing the discussion in the last part of our sessions. So, so next I want to invite Dr. Maud Ranau from the University of Sheffield, UK. So, Maud, are you there?
Yes. Yes, I'm
Okay,
here. Can you hear me?
Yeah. Yes, I can hear you. It's all your time. Please start your presentation.
All right. Yeah, thank you, everybody. And thank you, Hiroki, for inviting me and the whole board. So I'm going to talk about modeling building stocks for the circular economy today. It's mostly a presentation of our research framework because we have been quite slowed down by COVID and data collection. So I'm working on this with several colleagues from the University of Sheffield. A quick overview, I'm gonna quickly go through the traditional bottom-up approach to model stocks and what lacks in it for the circular economy. Then I'm gonna present the research framework and then a few concluding remarks. So far, stock research has been booming. This is a figure from a review we conducted a while ago. And you can see that most stock studies results are expressed in terms of weight of material, which might be a problem for circular economy. I'm going to talk about it later. This review also showed that we need to improve our knowledge on quite a few things still in material stock, mainly the amount, quality, and location of it, and when it's going to become available. But for these bottom-up studies, we are having problems of data quality and unavailability. So one of these conclusions from the review was to try to collaborate more with key data providers. Another conclusion was that non-residential buildings are an important share of the building stock, but they are not investigated enough yet. So a quick summary of the traditional bottom-up method. I'm going to try to get the laser pointer here. Yeah. So usually in a bottom-up approach like this, the basic equation is that material stock is equal to the inventory of items times the material intensity coefficient of each item. So what we do is that we have a building inventory, and then we classify all these buildings into archetypes. And for each of these archetypes, so archetypes will be what we call a typical building. For each of these archetypes, we then look at different building plans and building regulations and so on to try to calculate a material intensity coefficient for each archetypes. So this MIC is expressed in terms usually of kilos of material per dimensional unit. When we have this information, we compute this back to the building inventory, and we get the material stock of each item. We can then put it back into the geographical information system to have a geolocalized material stock. So the data collection is usually quite long, and we want to have the more buildings, as many buildings as possible in order to have the best material intensity coefficient, which is very time consuming. And the results of this method is that we have a geolocalized inventory that allows us to have results like this. I think Tomer in his presentation also presented a few others similar mapping of material stock. This is an example of a study in Odense that we conducted with Gangliu. Now, we have more and more geolocalized bottom-up material stock studies, and these results, as I said before, are at the material level. And this is, of course, already very beneficial because we understand the potential for secondary material, but we can also compare the accumulation between cities. However, what it does not do is inform the industry enough for circular economy strategies, because it is not enough for the industry to know how much glass there is stocked. They also need to know if it's in the form of windows, and if so, how many windows and what are the size. It's the only way for them to prepare and to design their buildings accordingly. So we are at the University of Sheffield, we are trying to find how to model these building stocks in more of a component level. So we have developed a multi-scale framework that allows us to assess the amount of stocks in buildings, but also the circular economy potential of this building stock. And this is because we want to provide information to the construction industry to help them shift their policy and practice. So the expected outcome is that we would have the locations, the quantity, but also a component level details of the whole UK's building stock, both residential and non-residential. So for now, we are doing a test study in Sheffield, and if this works out, we will scale it up to the entire United Kingdom. So I'm going to present the research framework now. So we have started working on this, but as I said, with COVID, we have some problems of data collection. So if you have any feedback on this research framework, this would be very welcome. This is, again, the traditional archetype method here. And we will try to complement the results of material stock for each building with some more component results. You are not supposed to read all the framework right now. I will go into details. We are also trying to include the circular economy potential in there. And the aim is then to compute everything back into GIS to get a secondary resource cadastre that includes component level information for each building, as well as their circular economy potential. So I'm going to detail first two main parts of our framework. So we have Marvel, which is a mobile sensing approach, and we have Regenerate, which is a circular economy tool developed at my department before I arrived. So first for Marvel, we have four different, Marvel is a vehicle that has a module on top of it that includes four different kinds of sensor. We have a visual camera, which is helping to detect and recognize envelope components of buildings. We have a thermal camera, as well as hyperspectral cameras, and both of them also can detect component material, as well as wear conditions of the building. We also have 4 LiDAR units on it that allow for accurate measurements of the size and geometry of buildings, as well as their envelope components. And this module is placed on top of a car here. And in this car, we also have a satellite system and inertial measurement unit. So we know exactly where the car was when it took each of its pictures. So then it's all about driving around in Sheffield. and taking these 4 kinds of pictures. And through a suite of machine learning and computer vision, we're able to first reconstruct the 3D geometry of the scene. So this is here. You can see that this is a quite nice rendering of buildings, but also to detect stock components and material. So this is an example here. And then we can merge both this information to get a semantically labeled urban model. Now we have started to test this vehicle model and its ability to detect components. So this is a bit technical and I don't exactly know how it works. This is another colleague working on it, but it's using an existing ensemble of convolutional neural network. So it's trained to identify building components. And we started to look at if it was working enough with windows and doors. So this here is a picture that was taken by the visual camera. And then the labeling scheme was divided in 8 categories. So the background that is not related to a building, then trying to recognize the walls, the roof, if there are any chimney, 2 variations of windows and 2 variations of door. And you can see here that it detected quite well the roofs in blue, the walls in red, the windows, the doors, and so on. Now, the model count, it took for more than 42,000 pictures, and we wanted to understand if it was doing a good job. So we also did a manual count on the same amount of buildings here. So we went through 1,360 pictures by hand, counting the number of windows and doors. You can see that the results from both the model and the manual count are quite close to each other in terms of mean windows count per building and mean door count per building. So we are quite happy so far with what we managed to do with Marvel. Now, so we are supplementing the data from Marvel back into the material stock inventory for each building that we get from the archetype method. So from the computer vision here in Marvel, with different information on each building, such as its height, the number of windows and doors, if there is a chimney or a basement, as well as the façade material. With the thermal vision, we can know if there is insulation or not in the walls. And then LiDAR information also can inform on more geometrical things like the roof angle and so on. So the concept is to develop very specific facade and roof material and component intensity coefficient, and to compute this back into our material stock results in order to get a more component level characterization of each building. And then we are aiming to compare these results as well, which should inform us on how accurate are the archetype-based estimation methods. The second part of our framework is the use of a tool, circular economy tool, which is called Regenerate. I put the link to it up right here if you want to have a look. So this is a circular economy engagement tool. So it is aimed at the industry to encourage them to design adaptable and deconstructable buildings. So if basically in the industry, if the designers input all their data into the Regenerate tool, it will assess how well their construction project fit into the circular building framework. So this circular building framework consists of a series of circular criteria that are split into 4 categories, namely the design for adaptability and for the construction, as well as circular materials and resource efficiency. And then these circularity criteria are applied to the core building layers. So site, structure, scheme, services. So this is a typical results that you would get from this tool. I'm not going to go into details here, but basically you get a summary of how many credits you got awarded by circularity principle here. And you can also get a more detailed results. So for example, in your design for adaptability, you can see, depending on the building layers, how much you scored. So this regenerate tool will be integrated to our framework. So first, we are also gathering data from the industry that will allow us to understand the circular economy potential and benchmark the circular economy potential of new build in the UK. And by doing this work, we will also see how to simplify the regenerate tool so it can be applied to our results of material stock. And hopefully we can get a better sense of the circular economy potential of the building stock in the UK overall. Then we can compute both this information into GIS, since from the beginning we have each of this information here, the component level characterization, as well as the circular economy potential. We should have this information for each building. So we can then compute it back to our geolocalized building inventory and get a secondary resource cadastre that includes both the component level information as well as an estimation of the circular economy potential. And these results will be sent back to the industry as well. Before concluding, oh, I'm good in time. Yeah. So before concluding, I will just emphasize our close collaboration with the industry. Oh. So a few points, key points. First of all, when we collaborate with the industry right now, we are focusing on getting data on non-residential buildings mainly, since data on public buildings or on residential buildings is usually a bit easier to access. So the non-residential buildings material intensity coefficient data is still quite scarce, but non-residential are quite interesting because they are believed to include more carbon-intensive materials such as metals. And also in the UK, there is a quite high turnover of non-residential, so they have a quite short life also. So this means that they are a clear key stock for the circular economy. So one of our focus is to find where to improve non-residential building designs. And if we find any information like this, we will flag it and share it with those that are working with us. About engaging the industry, this is taking a fair amount of time. So we released a data call that highlights mutual benefits. Basically, if you share building design with us, we will tell you the circular economy potential of your building. This is the main key point to engage the industry. We are, of course, following strict ethical guidelines that includes anonymizing data as well as non-disclosure agreements. For now, we have about 10, 12 companies on board. We got data for 15 buildings and we are expecting at least 30 more. I stress here that these are just for new built buildings and we are hoping to get much more information and data when the archives in the UK are opening again. So the data received from the industry, because they are new built or recently renovated, will be in the form of building information modeling. And this is one of my main new thing now working in Sheffield, is that I'm working with building information modeling. And it's quite nice actually, because this is a reference from a study on how long it takes to extract a bill of material from a building project. And manually, it's about 35 hours if we want everything, while with BIM, it's about 6 hours. So quite nice to receive BIM files and be able to analyze them quite quickly. A few concluding remarks. So as I said, our statues of research are hindered quite a lot, especially for the traditional archetype approach. For Marvel, our test results are promising. We are aiming to train the model now for material detection. And for Regenerate tool, well, it is already used by the industry and we are simplifying it. So apart from our contribution to the industry, there will be an expected contribution to the whole material stock research community. First off, we will have a new set of material intensity coefficient for the UK buildings, including non-residential material intensity. But we will also compare results at different stages in the framework, which hopefully should allow us to understand a bit better the uncertainties that we have when we use an archetype-only approach. And yeah, of course, these results are expected to be quite useful for the industry because we will tell them the location, amount, and type of components available. However, what is still missing, and this is a key thing that we will have to include, is when will these materials and components be available? And that's it for me. Thank you very much. And I hope you understood the whole framework a bit better, and I'm open for questions, of course.
Okay, thank you very much, Maud. It's a quite interesting talk, and maybe you are in the next stage and to estimating the material stock with the very up-to-date technologies as well.
Yes.
Wonderful. Okay, so now open for us. So if you have any questions, comments to Maud presentations, please let us know. And also very welcome to put it in your comment and question into the chat box of the Zoom. Anyone? Maud, could you give me some very simple information about in the last slide you said the BIM files?
Building information modeling.
That's a modeling. That's a modeling is perfectly automated now.
Yeah. So now it's in most architecture or building designers firms now, when they are developing quite big projects, there are many people on it, and they prefer to do it in these BIM softwares like Revit and so on. So many people can work on it at the same time. And then you get a rendering of the building in 3D, but also you can extract bills of materials from this. So for non-residential, which are usually big buildings, we have BIM models, and our collaborators there are sharing this.
Wonderful. Thank you very much. And another question from Jin from the Nagoya University.
Yeah.
Jin, could you turn on your video and also your mic?
Yeah. Yeah, thank you very much for your excellent presentation. So my question was already typed here. So I guess your research is very informative for the circular economy as a component level material stock. So I just curious that is it really practical to reuse or recycle the glass of the window, because I think it's very cheap. I don't know how about Europe, but in Asian countries it's very cheap. So is it very useful or effective to recycle it? Thank you very much.
Yeah, thank you. So useful, yes. Effective, I do not know. What I know is that when we conducted workshops, both in Denmark and in the UK, architects did point out that they would prefer this kind of information instead of just how much glass there is. The practical issues I cannot answer. I just want to highlight here that recognizing windows and doors is the first part of our Marvel vehicle training, and this is because it was obviously quite straightforward and we wanted to see if it works. But we will of course go into more details like materials and so on. Hopefully it works well as well. But yeah, I can only answer half of the question. So architects prefer to have the info in terms of components, that's for sure.
Okay, thank you.
Thank you.
Okay, thank you very much, Maud. Everyone, we still have some slot for the general discussion and later, the last part of our session. So if you have any question to the Maud right now, presentation, so please put your comment and questions into the, yes, we have one more question at the, oh, yes, Maud, can you see the?
Yeah, I see the chat, yeah. So Burak,
yes.
I would like to, this one could be used. I'm not sure, do you mean recognizing vehicles? Burak?
Hey, Maud, thank you again for the presentation. Yeah, for exactly, like using the same approach, basically collecting data on vehicles and using the same convolutional like CNN model, you can. I mean, have you guys thought of it, or do you see potential of this approach?
Yeah, we haven't thought of it because I work in the Department of Structural and Civil Engineering, so we are not much on per se. But I will put you in touch with the person really in charge of this convolutional neural network thing, and I think it would be better to ask him, as I'm not sure.
All right. Yeah. Thank you. I appreciate it. Good luck. Best of luck.
Thanks.
Okay, thank you. And also, Danny, this will give us some more information about the grass recycling. Thank you very much, Danny.
Thank you.
Okay. Okay, so then if you have any question more, then please type in the chat box as well, and then we will discuss in the later of this session. So I want to invite the final presentations by the Beijia Huan from the University of Shanghai for Science and Technology of China. Beijia, are you there?
Okay, thank you for the invitation. I am Beijia Huang from University of Shanghai Science and Technology. Okay. As you can see from the title that beside looking at the building materials, my research keyword here also at the environmental impacts. So my topic is basically introduction of our recent work that is published in the journal One Earth, a life cycle thinking framework to mitigate the environmental impact of building materials. Tommy is also my co-author, and Gao Xiaofeng, I see he's also in the conference. So if there's any comment in our discussion, I think maybe my co-authors can all together respond to those questions. Okay, I will move on. So as you can see in this figure that we account the global consumption of building materials from 2000 to 2017. And we can see that the building material almost tripled within the 15 years. And especially the concrete, aggregates, and the bricks are the most commonly used building materials. So you see the bottom side of the figure, we can see that China has the largest growth in this period, and almost all of the other regions, the proportion of the building materials all decrease. And for instance, Europe, the building materials proportion of Europe, decreased from 20% to 8%. So if we look at the life cycle of building materials, they from throughout their extraction, the processing, the transport of raw materials to construction, use, and eventually demolishing and waste. All the life cycles, they have the environmental impacts, and many topics are all focused to specific materials or specific value chain processes. But this discussion may have incremental or even diverse net environmental effects in other life processes. I will just give one example. For instance, the prefabricated building constructions, which is a very hot topic and practice in recent years. Within the construction process, it is definitely resource and energy saving, but there have been many claims that the prefabricated building, the construction, they will have extra environmental cost in the production and the transportation process. So we need to be very careful by looking at the environmental mitigation those proposals. And if we look at the traditional life cycle assessment, the framework is what we show in this figure. We need to collect the input and output inventories, which include the energy resources, the material resources, water resources, and all the emissions output from the different processes within the life cycle of the buildings, or say the building materials. And we need to collect the output inventory data. But we know that the buildings always have very long lifespan, which is always longer than 50 years or even longer than 100 years. So it appears to be very difficult to collect all the life cycle data among all the life cycle processes. So what we propose here is to address this challenge, we propose extending life cycle assessment to include life cycle thinking to explore roadmaps for mitigating the environmental burdens for building materials. And life cycle thinking here is more general than the life cycle assessment. It is more like policy networking, the more top-down planning. So as for the building materials, we raise here 5 main principles, which are identify key impacts and corresponding mitigation approaches, and emphasize building design and material selection through life cycle thinking, and effective construction and demolition waste treatment and recycling. And life cycle thinking to avoid pitfalls, which, as for example, I mentioned the prefabricated buildings. And then the integrating spatial and temporal aspects, which I will explain one by one in the following slides. The first one is identify key impacts and corresponding mitigation approaches. This figure, what we have conclude the key environmental emissions and impacts. So what we can find is that extraction and manufacturing of building materials activities resulted in almost 90% of life cycle environmental burdens, but these 90% do not include the treatment process. If we look at the treatment, for example, the waste plaster and the wood, they will emit emissions like organic acid in landfills. And the incineration of wood, plastic, and paper, they will all generate pollutants such as ammonia, heavy metal ions, and water-like organic compounds. This figure is from our previous work, which was published almost more than 2 years ago. In this research, we account the building materials in China within the recent 15 years, and we use life cycle assessment tools to estimate and find the key environmental impacts instead of climate change, which here we find that human toxicity is the top one, the most severe environmental impacts embodied in the building materials. And the most severe environmental burden materials are steel, cement, concrete. What we propose here is the published work most focus on the production process. And we think that more complete impacts determinations throughout building materials, the life cycle activities requires further, for instance, what I mentioned before include the treatment process, etc. Our second principle is here, we call it emphasize building design and building selection through life cycle thinking. I think Dr. Lano, our third presenter, has already mentioned the building design, the concept. Building design and construction can mitigate environmental burdens during manufacturing, construction, application, deconstruction, and recycling. Design for deconstruction will be is very important. It can easier disassembly and can easier recycling. The eco-labeled materials, for instance, the green building certification systems, including BREEAM, that is very common in UK, and CASB, our second presenter, Professor Malu Yama, he has also mentioned the CASB. CASB has very comprehensive life cycle assessment for the building materials and can evaluate the green buildings. And also the LEED, which is very common in United States and very common also in the whole world, I think. It also used the life cycle assessment for the building materials. Recently, we have finished the LEED proposal to get the credit by estimating the life cycle assessment for a chemical plant. And also the environmental product declaration, the short name is EPD, also is a very important tool to evaluate the building materials, the environmental performance for building materials. And recently we also working on the consultation from a door making company, as this is a Chinese company, but they want to export their product to outside. Including United States. So they are consulting how to prepare the EPD, and I think it will be a very hot topic. And our third principle is effective construction and demolition waste treatment and recycling. The effective sorting at the deconstruction source is very important. And life cycle thinking also requires special attention given to the high environmental burden materials, which I mentioned before, the concrete and the steel. The concrete waste typically comprises the largest fraction of construction and demolition waste, and is quite heavy. So we think that the on-site crushing and recycling is very essential, as it can help avoid energy consumption from transportation on this waste. This principle has already been practiced in the CDW management in China's policies. The fourth principle is life cycle thinking to avoid pitfalls. As I have already mentioned, for example, the prefabricated buildings is need very careful evaluation for its different life cycle processes. And the other examples also include, for example, the double glazed windows, the retrofitting, and the construction and demolition waste recycling, as they all will have some extra environmental cost in some process. So we need to be very careful. We need to identify the best decision for optimal environmental outcome. Our fifth principle is called the integrating the spatial and the temporal aspects. And by reaching this, we need cooperation. We need to use life cycle assessment tools together with material flow analysis and also the GIS tools. So it can benefit life cycle thinking by helping to further understand the energy demand and the environmental performance of building stocks across spatial and temporal scales. For instance, in this figure, we account the demolition waste, for instance, the concrete in different international regions. For instance, as we can see China, that the concrete will reach, the demolition concrete will reach its peak in around 2030. So which we call, we have to call that a supply demand analysis would be very necessary to avoid the capacity surplus for not only steel, but also concrete production. So some potential policy decisions may include restraining such lifespan buildings, as what Professor Maruyama has also mentioned, the policies and ways to longer the lifespan of buildings. So to conclude this research, we have proposed several life cycle thinking principles and practice to mitigate the environmental impacts of building materials across the life cycle different life cycle processes. But a further question here would be how to operate these principles effectively. So we need to understand the needs and the values of different stakeholders. By balancing the needs and the requirements of different stakeholders, it would be very challenging. Yeah, if we look at the buildings and building materials, the key stakeholders would include the building designers, the building material producers, the construction industry, building users, construction and demolition waste treatment companies, and policymakers. So we need to understand each stakeholder's concerns and design policies to motivate them to cooperate and promote the building sustainable development. Yeah, I want to close here. Professor.
Okay. Yes. Okay. Thank you very much, Beja. That's a quite interesting talk. That is quite important idea from the viewpoint of the life cycle thinking to discuss about the sustainability and also sustainable material stock and building materials as well. Thank you, Beja. That's quite interesting. So now open for floors as well. Any questions and comments from floors to Beja's once the presentation? Anything welcome? Or if you have any question, comment, you can put in the. Okay, someone. Yes, please.
I see Jean leave a message on site recycling or could be a potential. How much do you think can this contribute to improving the whole recycling rate in China? I think very large percent, as it has already been a very hot topic here. And this morning, I have just attended a key in Chinese it's called 重点研发项目，建筑垃圾重点研发项目. So, Chinese government has already funded some research projects to see how to recycle the construction and demolition waste. So there are already some pilot cities, and many cities has already issued the policies and the guidelines and many practice projects. So it has already very well practiced, I think.
Thank you very much, Beja. Jing, is everything okay for you?
Yes, that's it. No problem. Thank you very much.
Thank you, Jing and Beja. Any other question to the Beja? Right. Okay, it's thank you very much. Interesting talk, Beja. Someone want to have some questions? No? Okay, then including the Beja's presentations to think about for the whole presentation today, if you have any question or comment to the Tomel presentations and also Professor Maruyama's presentation and also Maud presentation as well. if you have any question, comment to them, please give us some comment and questions to us.
先生,
Yes.
can I have a question?
Sure.
To Maud, I'm very interested in the sensor of taking pictures and mount the sensor on the car. I'm quite interested in this.
Yeah.
But I wonder, so this study we only take pictures just by the side of the road. So
yes.
Okay,
Well,
so
no.
I think
we have discussed possibilities with drones, but this comes with a whole set of security things. So we are not there yet.
So this one is, I think, is a replacement to the we used to use remote sensing products, but this one I think is an alternative to the traditional ones.
Yes, so I didn't highlight either on the slide, but we will also work with satellite data. But COVID again, so this got slowed down, so I didn't talk about it. But hopefully we merge both.
So I have a concern. So if we can only take pictures just by the side of the road, so how about the buildings that which are not close to the road? So our vehicle with a sensor cannot get the picture of them. How
that's
are
true.
we going to deal with them?
That's a good question. So for now, we are testing the model to see if it works at all. If it works in the front of a house, it should work in the back if we manage to go in the back. But this, of course, is all about privacy and so on, and security reasons. So for now, we focus on checking if this model would work to get more component level information. If this works, we can try to approach whether the municipality or some kind of person who could help, and maybe try to continue. As I said, we discussed maybe mounting this on a drone as well, but yeah, as I said, it comes with a whole set of
maybe just ask the local volunteers to help you complete these tasks.
Exactly. Yeah.
Okay.
But yeah, we had these questions already. Thank you so much.
Thank you.
Thank you.
Okay, thank you, Jue. Any other questions from the floors as well? Or type in your comment and question to the chat box as well. Right. Of course, we can keep continuing these discussions on the website, and also have another session as well. But today, do you have any comment, questions? Tomeo, do you have any questions? You have the comments to all of us after hearing the another 3 presentations?
Oh, well, I think it's a great contributions from everybody. It shows all of the nice things that we're all doing. The question is if we can somehow integrate, because we're doing these things so independently, whether we can set up some kind of forum to mix up more our different methodologies and data and see if we can come up with new stuff. Maybe that's a thought that comes to mind, I think, after this session.
Thank you very much, Tomeo. Yes, that's true. And also, we want to have the 1 or 2 words from the speakers as well. Mariama Sensei, Professor Mariama, do you have any comment on some things to our whole sessions?
Yeah, it was very thank you very much for giving me a chance to talk and have a chance to learn from your the field of sustainable material stocks. Now, yeah, I have some idea to how to cooperate, but well, still I need to learn many things. But yeah, thank you again. Thank you very much.
Okay, thank you very much, Marino Sensei. Then Maud, any final word from you?
A big thank you, first of all. And also, yeah, I agree with Tomer that it would be good to try to work all together or find a way to do that. I think it was easier to chat about this in person in ISIE conferences. We had taken kind of a habit to meet there every year. So let's hope when things go back to normal, we can maybe do that again, and it could be easier to develop collaborations and overall knowledge. Yeah. Thank you again.
Yes, thank you. Thank you, Maud. Beijing, any comment and words from you to all of us here?
I think it's my first time to attend this kind of session. Maybe I'm thinking I didn't have a very formal schedule. I think maybe some of my colleagues do not have a very clear access to this kind of session. So maybe we can have some more formal schedules so we can circulate to more people, so more people can have the chance to attend and communicate. That's what I'm thinking. And I also looking forward for further opportunities to communicate and cooperate to you and to other researchers. And that's it. Thanks. Thank you for inviting me here.
Okay, thank you, Beijing. And thank you very much for all four presenters. We have a very nice time to thinking about for the towards sustainable material stock. So and also thank you very much for everyone here on the Zoom and also YouTube. And we have the very interesting session of the session 6 of the SEM Power Pressure online conference. And finally, I want to announce for the another Power Pressure conference of the SEM, ISIE SEM, that we keep continuing the ISIE SEM conference online. And also that you can check previous or past our sessions on YouTube, so that you can access from the YouTube channel of the SEM. And also the next session we will announce very soon in the ISIE SEM website on the web. And also we are very looking forward to having the future sessions of SEM and also Oceans, and also the special session organized by the SEM members as well. And we are planning much more about for the online publisher conference. So thank you very much again, everyone, for joining today. I hope you all being safe and well rest of days. And also we are very looking forward to seeing you very soon online and physical conference maybe next year or 2 years from now. All right, thank you again. Thank you very much for all speakers, and thank you very much for the all attendance here. Thank you very much.